attending Big Data Day LA. Feel free to take pictures, and the hashtag is DataConLA. Post it on social media. So our next presenter is Justine Cocchi from Microsoft. Justine is a software engineer at Microsoft working across the nation and around the globe to be successful on Azure's data platform, organizational cloud data open source for data processing. She will be presenting a talk titled Graph Computing, How the Gremlin Stole Christmas. Please join me in giving a big Data Day welcome to Justine.
Hi everyone, thank you so much for coming. As he mentioned, I'm Justine and I'm a software engineer at Microsoft. This is going to be a very 101 intro to graph computing, what graphs are, and a way to process them. So let's get started. This is how the gremlin stole Christmas. Before we get into graphs though, I want to kind of level set with the audience. So I'm going to assume that everyone has a pretty good understanding of relational databases. Is that true? Yeah? Okay, so let's go over that a little bit and unpack it. So for a relational database, all of your data is stored in tables. And your columns define the shape of that data, with each row being a record, right? So when you have a record, you know exactly what properties are going to be in it. You know exactly what columns, and you know what your data looks like. So to visualize this, we have a table. So this is a table of children. Children that Santa's going to give toys to, and we've listed exactly what toys he's going to give. So let's add a little bit of complexity though. We want to separate out fields for use in multiple places. This avoids duplication and allows for easier updates, right? So say Santa's also keeping track of all of his elves and what toys they're making. So let's go ahead and abstract out toy into its own separate table. So now we have these foreign keys. We have this foreign relationship, right? The children are related to the toys, and elves are also related to that same toys table. But Santa's a pretty complex guy, and we want to add a little bit more complexity to his database. So we're going to add some many-to-many relationships, right? So this adds that mapping table in the middle. This mapping table doesn't really represent anything. It just kind of represents the relationship, the many-to-many relationship between either children and toys or elves and toys. So many children can receive multiple gifts, and many elves can make multiple toys. So let's review what we know. Many children can receive many toys. Many elves make many toys. But toys are made up of parts, so we should probably model that as well. And that gives us a new mapping table. And these toy parts are made in workshops, so we should keep track of where everything's being made so we don't forget anything, right? And elves can work in workshops. So many elves, maybe they work in different workshops on different days. We want to keep track of their schedule, so we have to model that as well. And can elves make part of a toy though? Do they have to make the whole toy at one time? They can probably make parts, right? This seems like it would be much more efficient if we can let them make just specific parts. And maybe children can receive parts of toys as well. If we have a doll, maybe she's receiving an outfit and not necessarily the whole doll every time, right? So children can receive parts. But what about Santa and his reindeer? And this is really complex, and now we know why the Grinch stole Christmas. It's way too confusing, right? So how do we simplify this? Santa doesn't want to have to manage all of these many-to-many tables and all of these join statements, and Santa's not very good at SQL, so how do we fix this? So at this point, I have to admit that I lied to you. This talk is not about how gremlins stole Christmas. This is how the gremlin graph saved Christmas. Wait, what about giraffes? No, I didn't say giraffe. But there is something called Apache Giraffe, which is a graph processing engine. We're not going to get into that today, don't worry. Oh, graphs, okay. All right, so what is a graph? What are graphs made of? Graphs are made of vertexes and nodes, right? So this represents all of the data in your system. You can think of these like the rows in your SQL tables. And we have two data points here. We have Cindy Lou Who, she's a child, and we also have dolls, which is a toy, right? So instead of tables, we just have vertexes. We just have, what the data is. And this data can be related, right? So we have edges, and these edges define the relationship between our two vertices. So we have an edge from Cindy Lou Who, and she receives a doll. So this edge is the received edge. But the beauty of graphs is that you can add to them on the fly. So say we have dolls, but we also have trains. So Cindy gets a doll, and she gets a train. And when we add it, we're just adding essentially new documents to our database. So all of this would be represented as documents. And the important thing to recognize here is these edges have direction. So the receives edge is coming out of Cindy and into train. So the direction is important. And the other thing that's important is that edges are first-class citizens. So unlike in SQL, when you're creating an edge, it's really like a join statement. Do I need this? Should I put, it's like cutting out. Can everyone hear me if I don't speak with this? Okay, let's just do that. I will project. So the edge is that first-class document, right? It's a first-class citizen. So receives would be a document itself. If you think of how this is actually stored in your database. Your Cindy Lou Who is a document, receives is a document. So this makes it really fast to traverse your graph and perform really computationally expensive things. In SQL, it might be a whole mess of join statements, but in graphs, you're really just linking documents together. So this is why graphs work really well with highly connected data. And you can add new connections on the fly. So say Cindy receives a doll, but she also plays with the doll. So let's add a plays with edge there. And these graphs, the graphs that we're talking about today specifically, are called property graphs. So what does that mean? There's key value pairs that will describe either the vertex or the edge. So one very important key value pair that you'll always have is the label. So I don't have it listed here, but the Cindy Lou Who would be labeled child. Doll would be labeled toy, as would train. But the labels are listed for our edges. So receives is the edge label, and plays with would be the other edge label. You can have an unlimited number of these for each type. So say we want to add a couple properties to some of our vertices. We have Cindy, she's age 5. Trains take 5 hours to make. Dolls also take 5 hours to make, but what if we want to store more data about dolls, specifically the hair color? You can add that as well. And you can add any type of property. It doesn't have to be synonymous. So like the train doesn't have a hair color, right? It doesn't have to follow one label doesn't have to have all the same types of properties. Edges can also have properties. So a really common property type for edge would be something like a weight. And this would be really useful in computing all sorts of things. We're going to look at weight a little bit later. But it doesn't have to be weight. You can add any type of information. So let's say we want to keep track of what year Cindy received her train. She received it in 2017. Okay, so we learned a little bit about graphs, and we learned about the structure of the graph specifically. But graph computing really is a combination of two things. It's that graph structure, but we also care about the process or the traversal, right? Graphs themselves as a database, they're not useful unless you can query them. So how do you do that? What are gremlins for? Gremlin is actually the query language. So you can think of Gremlin like SQL for relational databases. There are a couple different query languages. Another really popular one is called Cypher, used with databases like Neo4j. But today we're going to focus on Gremlin. So Gremlin is part of the Tinkerpop stack, which was developed in 2009 by Apache. And it allows you to query your data and express the properties of your, or express traversals of your property graph. So what is the Tinkerpop stack? I'm not going to go into this in too much detail, but essentially the Tinkerpop stack is made up of a bunch of different pieces that all come together, and Gremlin is just one piece of that. So the top level, we have Rexter. This is your Gremlin server, and it's the server that's actually exposing your graph via a RESTful API. So this is what allows you to actually query your graph. If you were submitting remote scripts or something, this is what you're interacting with. Gremlin, we already talked about, is that graph query language. Frames are the maps between domain objects and the graph nodes. So you can think of this like an ORM, or object relational mapper, for SQL. It's what's actually translating the data that you're using with the actual nodes themselves. Pipes is like the data flow API for processing the graphs. Blueprints are an agnostic property graph model. So this is really important. The fact that it's agnostic means that you can use any underlying graph engine with this stack. And the furnace is some common graph analysis algorithms. So for instance, there's a whole set of algorithms represented around machine learning. So these are just some common things that you can use. And all those components build on each other. So let's shift back to Gremlin a little bit, though, and let's take a look at the Gremlin Traversal. So I already told you this is how you derive value from your graph, right? And there are 5 main traversal steps that you can take. The first would be map. So this is essentially everything, take all of your object and just emit a transformation of it. So you're not really doing anything, you're kind of just emitting it back out. And we're going to look at an example of all of these, so it'll be a little bit more concrete. But this would be something like list all vertices. So just show me all the vertices in the map, or show all the edges in the graph. And then we have flat map. So this is similar, but it's just flattening it, right? So imagine you have the incoming object, and it's iterating over that object and just giving you a flat map of your traversal. And then next we have a filter step. So this is take everything coming through and decide whether or not it can pass. Filter would be, maybe you want to filter on property, so if it has the name property, or if it has a certain age, right, you want to filter your graph. And then we have a side effect step. So this is essentially let everything that's coming to me pass through, but give it some side effect. So one example would be add a label. So maybe you want to mark all nodes that you've already seen as seen, right? So we can remember what we've already seen and maybe not include it later, or include it based on some label that we're giving. And the last step is branch. So this is basically split the traverser and send it to a new location in the traversal. You're making a decision about which step to take. We're not really going to cover branching today, but those are the main types of traversals, and everything that you can do is one of these 5 steps. So how do we actually perform this? There are, as we said, Gremlin server, you can submit remote queries, but a really nice, easy way to get started is the Gremlin Console. So the Gremlin Console is an REPL, which stands for Read, Evaluate, Print Loop, environment that lets you immediately create, query, and manage your graph. So we're going to take a look at the Gremlin Console in just a second, but this gives you the ability to connect to many graph systems. So if you want to use some other underlying database, that's fine, but we have something called the Tinker Graph, which is an in-memory graph, which is really easy for getting started. So we're going to work with the Tinker Graph today. And there are a bunch of toy Tinker Graphs that are given to you when you download the console with some simple scenarios that you can perform traversals on just to kind of learn and get started, or you can start from empty and create your own. So that's what we're going to do today. I just want to quickly go over the graph that we're going to be traversing. So this is the graph that we're working with. This is, imagine, Santa's database. It's really small. We have a couple children up there. So we have Cindy's, number 1. We have Ralphie, and we have Charlie. And I have some locations. So Ralphie and Charlie live in San Francisco, while Cindy lives in LA. And then we also have toys. We have doll and we have train. So we're keeping track of what toys these children are going to receive from Santa. So at this point, let's actually take a look at the Gremlin console. So I actually need to restart this. I'm going to open a command prompt, and I'm just going to navigate to where I have my console installed. And I'm going to type in gremlin.bat to actually start the Gremlin console. And I have a list of queries that we're going to run today, cheated a little bit, saved them all so I wouldn't have to type them. Okay, so you can ignore these warnings. It's just some Java versioning errors. But the first thing we do when we open the console, we don't have anything yet, right? This is just the Gremlin console, so we want to actually create a graph. So I'm going to copy this. Graph equals tinkergraph.open. So remember, tinkergraph, I told you, is that in-memory database. And .open, we're just going to open a new empty graph. So this is going to be the API to the structure of our graph. Remember, graphs, we have structure and we have traversal. So let's work with the structure first. And let's actually add some vertices. So let's create the vertices that I had on my example earlier. Oops, not that. We already have that. Let me and then let's paste these in. Oops. Wait, hold on. Sorry. Cindy. Oh. Oops. Sorry, anytime you're trying to do anything live, it always goes wrong, right? All right, let's copy. Now we're going to paste. OK, So now we have some vertices in here, and I'll just go over what one adding looked like. So let's take a look at Cindy. Is this big enough? Can you all see this? Okay, cool. So if we have Cindy, we're creating a new variable, and we're looking at this graph. So remember, that's the API to the actual structure of the graph. Add vertex. So we're going to add a vertex to our graph structure. And what is that vertex? We're giving it an ID, so Cindy is number 1. We're giving her a label, so this is a child vertex. And then we're going to add some properties. So we have a property name, and the value is Cindy. And we have a property age, and the value is 5. So if you wanted to add more properties, you just keep going, kind of, comma, add whatever you want. And I've done that for all of the children, the toys, and the locations. So now we have our vertices. Let's add a couple edges between these vertices. We wouldn't have a graph if it wasn't connected, right? So, no, not that. Copy pasting is always a challenge, apparently. All right, copy, paste, cool. So now we've added a couple edges, and let's take a look at what that looks like. So we have Cindy, we have our Cindy object, and we're going to add an edge to her called receives. And what is she receiving? She's receiving that doll object that we already created. And we're going to give this an ID as well. It's going to be ID 8. So I've done that to model the graph. So after running all of these steps, we now have something that looks exactly like this. This is what our graph looks like. But how do we know? I don't expect you to just trust me. We want to actually create a traversal source, right? So we have that graph is that structure, to the API to the structure. We want to be able to actually traverse it. So let's add our traversal. G equals graph.traversal. So graph is the graph that we're working with right now. .traversal, we're just creating a traversal source, and we're naming it G so we can use it later. So what can we do with this traversal source? Let's take a look at all the edges that we've added. So G.E, oops, not that. Oh no. Oh man, that typing is very difficult. Luckily, I've copied everything, so I can just copy it back over. It'll be really fast. All right. We're going to copy this back. We're going to add our vertices. Okay, let's add our edges. Does anyone have any questions so far? No?
Does it have to be added in sequence?
It doesn't have to. Like, your vertices don't necessarily have to, but your edges, obviously you can't add an edge. Sorry, I don't know who asked the question, so I'm like looking generally. You can't add an edge between two vertices that don't exist. So that's the sequence. Yeah. And then I'm going to recreate our traversal. All right. So now we've looked at all of our edges. I don't think I actually ran that. So let's do G.E. And we get a printout of all the edges that we have. So we see 1, remember that was Cindy, and she receives 4, which was a doll, I think. So that's pretty cool. We can see all of our edges, but that doesn't really tell us anything. What if we want to know how many edges we have? This is really short. Obviously, we can just count them, but it wouldn't be recommended to run a query like G.E on a really large graph, because that's a really computationally expensive thing. Maybe it's iterating over a ton of documents. So what if we want to do something else like count? Let's do G.E .count. And we'll see we have 7 edges right now. And now let's take a look at one of our vertices. Let's look at vertice 3 and see what's contained in there. So this is Charlie, and we're getting a value map. So we're basically getting a value map of all the properties that Charlie has. So we have his name and we have his age. It's kind of interesting. But what if we want to know about all of our vertices? Like, what labels are there? What types of vertices are in this graph? So we have G.V.group_by_label. So again, G, that's our traversal source. So we're starting at the root of the graph. And .V means give me all of the vertices that exist in this graph. .group, we're going to group them. Okay, but what are we grouping them by? It's that .by step, and that's label. And that would be something like that side effect, right? The group by. We're telling you what to do. We're passing everything, but we're going to add some side effect. And we have our location. So we have location, child, and toy. So now we see the groups, and it's a little bit easier to read rather than just printing them all out, right? So what if we want to do some other computations on our graph. So what if, Santa is thinking about this and he's like, I need to make all my toys. What's the oldest kid? So how old am I looking at here? Let's figure out the oldest kid in this graph. So again, we have g.v, so we're looking at all of our vertices, dot values, so anything with an age value, and then just take the max. So the max is 8. The oldest kid is 8 years old in this database. Now, let's drill into just one vertice. Let's actually take a look a little bit closer at Cindy. So first we have to find Cindy. Oops. Let's do this. So g.v, again, look at all of our vertices, dot has. So any vertice that has the name property equal to Cindy, and then output that. So you can imagine our little gremlin standing right here on this Cindy node. So we're looking at Cindy, and what if we want to know, okay, well, what gifts is Cindy going to receive this year? So let's copy this query, not that query. And if we unpack this query a little bit, we have g.v has Cindy, so we're finding Cindy again. And then out e. So if you imagine a little gremlin standing on that edge, the receives edge. So all of her receives edges, just imagine a little gremlin standing right there. And then in v. So if we have Cindy, out e, we're standing here and here on these receives edge, in v. So then we're going to stand at 4 and at 5. So the in vertex from that edge, and then we're going to take the name, the name value. So then we get our doll and our train. So it kind of helps to imagine like a gremlin literally standing and how he's traversing on the graph itself. So we have all the gifts that Cindy will receive. And if we wanted to simplify this query a little bit, we're going out e and then in v of the same edge. So to simplify it, we could just do, instead of out e and in v, just say out. And it produces the exact same thing, but it's just a little bit easier. It's like a shorthand way of typing it. So now let's see who lives in the same city as Cindy. I'm going to copy. And let's see. Who lives in the same city as Cindy? So if we take a look at this query, we're looking at all of our vertices. We're finding the one with the name Cindy, and then out lives. So now we're standing on the actual vertex of where she lives, and then in lives. So where she lives, but then all of the vertices that also live there, right? And then we're getting the value. So here we get Cindy and Ralphie. But it's kind of clunky to say that Cindy lives in the same city as herself, right? That's a little bit weird. So let's find out a way to exclude her. And I'm going to copy this query. All right, and now we just get Ralphie, but let's actually unpack this. So g.v has name Cindy, so we know how to find Cindy. And we're doing this dot as exclude. So we're adding a label to this value, and we're excluding it. So we know we've already seen this. We don't want it to arrive in the list later. Out lives, so this part is the same, right? So where she lives, and then all the vertices that also live there. But now we're adding this where doesn't equal exclude. So this exclude is a label that we added. I could have named it watermelon, right? It doesn't matter, but then you just have to look for that label again on the other end. And then we're getting the value. So now we just have Ralphie lives in the same city as Cindy. But what if we want to see, okay, so what are the actual toys? Let's say we know that Cindy lives in San Francisco or LA. So let's say, like, what are the toys that are actually going to be delivered there? Like always one behind. So I'll just go ahead and copy and paste this. So if we want to see all of the toys that are being delivered to LA, we again start at that graph traversal. We're looking at all of our vertices. We're finding the LA node, and then we're finding who lives there. Out receive, so what are those people receiving? Values name, so just get the name, and then group count, so how many of each type. and we get there's 1 doll and 2 trains being delivered to LA. So this is how Santa can kind of plan his route. And similarly, if we want to do something else, like see how many children are going to receive trains, maybe he wants to know how many trains do I have to make this year. We can do a query like this. So 2 trains, and if we unpack this, graph all of our vertices with the name train in receive, so everything that's receiving a train, and then just count them up. So now we can kind of look at some of these basic Gremlin queries, and we know a little bit about how to actually traverse our graph. So if we go back to the presentation, and now I want to talk a little bit about Cosmos DB, and I obviously love Gremlin little GIFs up there, and that's actually the Cosmos DB logo, so if you're wondering. There are gremlins hiding everywhere. So what is Cosmos DB? Who's actually heard of Cosmos DB before? Anyone? A couple of you? So Cosmos DB is Microsoft's multi-model globally distributed database. And it has a bunch of different APIs that you can use to access it. And this is what makes it truly multi-model. So we have a SQL API, which is actually NoSQL under the hood, but you can query with SQL-like syntax. That's the DocumentDB API. There's a MongoDB API, which is essentially MongoDB as a service. There's a table API, so that's for key value pairs. A Gremlin Graph API, that's what we're using today. And a Cassandra API for that key value wide column implementation. So today we're going to focus on the Gremlin Graph API. And if you want to see, I have a Cosmos DB instance already created. So I logged into the Azure portal and already created this Cosmos DB account. It takes a little bit to deploy, so I didn't want to bore you guys with that. And if we go into our Data Explorer, we can see that I don't have any databases yet. So let's go ahead and create a new database. And I'm going to name this Big Data Day. Okay. And once we have our database, we can actually create a new graph. So this is kind of like a collection of documents. So this is what our graph is going to be like. And let's give it a name, and I'm going to name this Santa's graph. This storage capacity, fixed versus unlimited, is basically a partitioning strategy. So if you have a really large graph, you want it to be partitioned so that it can scale and you can query more efficiently. Today we're just going to use fixed. So essentially that means it gives you 10 gigabyte bucket and it's just one partition. So we're not going to use partitioning today. And for throughput, let's just say 1,000. Okay. So let's create this graph, and we see it here. And if we click on graph, it's empty right now. So I have an application here, and this is actually provided to you from the Getting Started. So if you want to get started with a new application, there's this quick start here. I just downloaded the quick start. And let's kind of walk through this program a little bit. This is a .NET application. I've opened it in Visual Studio. And we have our main function. So the first thing that we're doing is we're actually creating this document client. So this is the really cool thing about Cosmos DB. Because it's multi-model, you can query your graph with different APIs. So we're going to be using the SQL API here, but we're going to be creating graph objects. So we're really using that multi-model capability. We're creating a connection to our database, and we're running our program. So what's in our program? We're connecting to our Big Data Day database. We're getting our graph collection. And then we're going to add some Gremlin queries to it. So the query syntax here is a tiny bit different, but it's very similar to what we entered into the Gremlin console. You can see we're doing things like adding our Cindy property graph. We added her age here. We're adding a bunch of edges. And we're going to loop through all of these Gremlin queries, and we're going to create a key value pair, and we're going to create that document query. So this is what's going to actually write all of our documents into our graph. And then here we have all of our Gremlin queries, and we're going to submit. We're going to submit these properties and actually create the graph. So I'm going to run this application. And we can see it running here. It's adding all of our edges. We hit the end. I'm just going to continue through that. So once we've run this whole application, we now have our graph loaded in here. So let's just take a look at some queries. G.v. So remember, this is our traversal source, and g.v give me all of the vertices. So it's a little bit easier to see in this representation, but this is what the console is doing too. And we have this really nice graph here, so we can look at all of our connected vertices. So we have our Cindy vertice, we're starting here, and Cindy is receiving a doll, so we can go click and we can look at the doll vertice, and it gives us all of these properties here. So this is Cindy, and we have these properties. We have her label, her name, her age, and it's giving you these targets. So what are her edges? She's receiving this doll. If we click here to Charlie, we can see he has some edges as well. So this is just a really nice way to view your graph, and this is just to show you can use these Gremlin queries either in a real hosted database like Cosmos DB or in a toy one with the Gremlin Console. Okay. So we talked a lot about Cosmos DB. And graphs and how cool they are, but should we always be using graphs? I mean, it sounds like they're pretty powerful, right? Is that the one-stop shop? The answer is no, obviously. You want to model your data, how it makes the most sense for your application. So if we look at relational databases, what they work really well for is if you have predictable data. If your data really does fit into that row, column, table structure, then that's probably a good choice for you. If your queries aren't super join heavy, or if you just want a really mature data model with a higher assurance for your transactions, your recovery, and durability. Graphs, however, have a very adaptable schema. So if you want to be adding new property types and new labels and new things on the fly, it's really easy to do that with graphs. Graphs are to be used when the relationship is at least as important as the data itself. So these are very join-heavy, very connected systems. So if you think about the canonical example for graphs is a social network, right? Who I'm friends with and me, myself, we have similar weight. The edge is a first-class citizen in that data model. So some real-world examples. This is useful for social networking, for fraud detection, a lot of identity and access management, but it's also really useful for real-time recommendation engines. So let's go ahead and build a super simple, very slimmed down recommender to help Santa give better presents, right? Santa wants to be a cool guy. He wants to give you what you want. So we're going to take a look at a smaller subset of our graph. And we have Cindy here, and she's still receiving a doll, but now we're going to add a new edge, and it's called likes. And we're going to give it a weight. So she likes this doll 9 amount. And Ralphie also likes dolls. He likes them a little bit less. He's at an 8. Cindy likes trains too, though. And if we want to recommend one more toy for Ralphie, one way to look at it would be, okay, so Ralphie likes dolls. Who else likes dolls? And then what else do they like, right? I want to recommend what they like to Ralphie. So we hope that we can create this edge. So let's see if we can recommend a train to Ralphie. And let's go back to our console. Oops. Let's go back to our Gremlin console. And it looks like it's mad that, okay, I'm just going to have to create a new one, but that's okay. It won't take too long. All right, let's run our console again. And we're going to recreate this graph API, so the structure to our graph. We're going to add our vertices back in. We don't actually need all of these, but I'm just going to add them in to be quick. We'll add them all. We're going to add our edges back. And let's get that API for our graph traversal back. Okay, so now we have the structure of our graph. And for our recommender, we're going to add a couple more edges. So we'll just take a look at one of these. This is exactly what I modeled up on the board, but we have Cindy, and she likes her doll. So we're adding that, and we're adding that weight back in. So we have all of our edges now for what Cindy likes and what Ralphie likes. Now let's go ahead and find what does Ralphie actually like in this graph. Oops. So we're going to copy this. And then Ralphie likes dolls. Okay, cool. If we want to unpack this statement a little bit, we have g.v, so again, look at all of our vertices, has name Ralphie, so we're finding the Ralphie vertex specifically. Out e likes, so what does Ralphie like? And now we're standing on that edge with the weight greater than or equal to 7. So this is one case when you wouldn't want to just use an out because then we couldn't add this weight, right? So this is a use case for adding that out e step. We can get any weight that's greater than 7, and then in v, so that vertex itself, and then the name. So that's how we found our doll. Okay, so we know what Ralphie likes, but we want to know who else likes what Ralphie likes. So I'm going to copy this new query. Oops. And let's unpack this a little bit. So we have our graph traversal source, we have all of our vertices, and then we're finding Ralphie. We're going out e likes and what he likes that's greater than 7. So this is the same, right? And we have in v. But now that we're at what Ralphie likes, we want to go in e. So who are the other people that like that? Where's that relationship? And then we have another has operation, and we're getting weight greater than 7. So we want to make sure that they actually like it. It's not enough that they have that relationship, but it has to be an appropriate weight to us, right? And then out v, so what's that vertex? And then we're getting the values. So we have Ralphie and Cindy returned, and I showed you how we can use that exclude to get rid of Ralphie. You know, Ralphie likes what Ralphie likes. It's kind of clunky, but I didn't add it in here just for simplicity's sake. So now we know Cindy likes what Ralphie likes. Okay, so that's cool, but we want to actually recommend a toy to Ralphie. So this is the last query. Let's go ahead and copy this, and then we'll unpack this one. Oops. All right. So we got train, which is the expected result, but let's actually go through it because this is a pretty complicated query at this point. We have g.v, so all of our vertices, has name Ralphie, so now we're standing at Ralphie. Out e like, so what does Ralphie like, with a weight of 7. And we're going to exclude this node. So we already know what he likes, we already know what he has, he's already rated this thing, so we don't want to recommend it to him again because he already has a relationship to it. And then we get the in edge likes, so this is where we're standing at that actual object, and we're making sure that the other people that like it have that weight greater than 7. And we're standing on the out vertex. So now we're at like Cindy, right? And then out e, what do they like with a weight of at least 7? So making sure they actually like it, not just that they've rated it, but that they actually like it. And then in v, so now we're at train, and where we haven't seen it before, so we would have been at train and doll, right? But we've already seen doll, we already excluded it. And then we're getting the values. So now we have train. I know that's kind of a big one, and this is a very simple recommender, but it just shows you the power of graphs and how you can traverse them to get really rich and meaningful data, even as something as simple as our graph. So that brings us to the end of the presentation, and I just have a couple of resources here. You can take a picture of this slide if you want. The first link is a link to the Tinkerpop documentation itself. And I have up there, for lots of giggles, read the first 3 sections, Tinkerpop 0 through 3. I just thought it was really entertaining. So give it a read if you want a little laugh. If you want to get started with Gremlin, this tutorial is awesome. I used a lot of things from this tutorial to make this presentation. And lastly, if you're interested in Cosmos DB's Graph API, I have a link for that as well. So thank you guys so much. I hope you learned something. And yeah. Do we have any time for questions?
Well, there's like a 10-minute in between.
Okay.
But we're waiting for the next presenter.
Okay,
Yeah.
cool.
So thank you, Justine, and please give us feedback with the meeting app, and please visit our sponsors who are in front of Beauvoir Auditorium. They really help make this event possible. And our next topic will be AI-powered customer analytics in the age of GDPR